It's time for another math easy solution. Today I'm going to go over further into gyrocompasses and now look at how gyrocompasses work, plus corrections to my earlier videos. And yeah, this is more of a clarification on gyrocompasses because I made some mistakes in the earlier videos. Anyways, and like always, you can download these exact notes and link the description below, and you can view these notes as an article on the Hive blockchain and so on. And you can play this video at faster speed and so on. I'm just going to continue on here. So MES Note, I started doing debunking flat Earth videos, and the first videos were on the gyrocompass. After making those videos, I realized that I made some slight errors regarding gyrocompasses, so that I will clarify those here, or so I will clarify those here. Note also that I will update the relevant video playlist to include this correction, and those can be seen on MES links. And you can go over here, MES links, mes.fm/links. You can click this drop down, and then you'll see the MES experiments. I'll put the stuff there, anti-gravity stuff, and the debunking flat Earth right here. Now I'll include a link to this video that I'm doing just because I made mistakes in those relevant videos. Anyways, continuing further, so topics to cover. So we're going to go over how gyrocompasses work, gyroscope properties, they have the rigidity in space, precession, and an important note, high spin speeds overcome small torques, and how gyrocompasses detect true north, and then further corrections to my earlier videos. All right, let's continue further. So how gyrocompasses work. So a gyrocompass is a spinning wheel with 2 degrees of freedom and a mechanism to induce precession to determine true north. Or geographic north. This is basically the spinning pole. So like the imaginary line, you look at they'll have a pole on the top and bottom. All right, and a gyroscope is a spinning wheel with 3 degrees of freedom. So this is important. So gyrocompass is 2 degrees. It says 3 degrees is just a regular free gyroscope or gyroscope, right? Just in general. Yeah. So here is a free gyroscope, and this can be rotated about 3 different axes. So you have it spinning here in this this brass color. Then so it can rotate about this, like that. So that's one spin axis. Then it can rotate about this one right here, across here, and then finally it can rotate about this right here. So that's 3 there, and there's a GIF that we can play. So let's play this GIF. Okay, right, so here's a GIF right here. Zoom in, make it bigger. Yeah, so basically you can see all those moving, and then it wants to maintain its orientation and so on. So that is a gyroscope with 3 axes of freedom, or semi-freedom. It's just that it can overcome the bearing friction there. And now here's just a typical setup for a gyrocompass, but it's not really a gyrocompass. It doesn't have an induced precession setup. So image here, so a spinning wheel with 2 degrees of freedom instead of 3. So this can only spin about this axis like that. It can spin about that. And then this can spin down right here. The only thing it can't do is spin about this axis, but the horizontal. So there's no horizontal line. It can't go upside down like that around that axis. Or actually, better yet, if I draw it like this. So this can't spin about this way. So it can't just turn up. This whole thing will be stuck. So that you can't have these on the top. So this is only 2 axes of freedom. That's again along this axis and along this axis. That's the only ones it can spin. All right. And technically this is a gyrocompass, but this doesn't have a mechanism to induce precession, so I wouldn't call it a gyrocompass. And also this basic setup has high friction. These supports aren't even bearings, they just connect metal to metal. And this one right here, just a metal piece inside just a circle there. So again, it's just metal rubbing on metal, and it's it's a high friction setup. All right, let's continue further. So gyroscope properties. So the gyrocompasses uses 2 main properties. So gyroscopes have 2 main properties: rigidity in space, and the next one is precession. So let's look at the first one, rigidity in space. So gyroscopes want to maintain their orientation when torqued, and just torque is just a rotational force or pair of forces that causes a turning motion. So if you have just an axis over there, and this definition of a coupled or coupled forces, you have a force up and down, so you have a twisting motion. So that's a twisting force, well, it requires two forces. So let's image torque as a force couple. Then here's torquing a car tire nut. So you're going to have to go down here and this up, etc. So if you're tightening it or loosening, etc. All right, and now here is a demonstration of a gyroscope resisting changes in orientation. This is by a Professor Walter Lewin right here. And so this video here, I have a link on my MES Links Telegram. So go over here and play it. Let's play this.
This is the basic idea behind inertial guidance systems.
I'm just going to fast forward here.
Manage to get that torque on the for spin.
Okay, once he spins it up, then this is just a free gyroscope, and then he'll move it around.
The frame will rotate.
Okay.
The pilot.
Okay, spinning up.
Oh.
Okay, let's just get it spun up.
Angular momentum.
All right, so it's high.
I'm the airplane.
Yeah, it's just a spinning.
And I'm going to fly. Look at that spin angular momentum. It has no respect for me. It stays in the same direction no matter how I fly.
Oh, yeah, so basically, yeah, it just moves it around and so on. All right, here I quickly went over to the actual YouTube video and you can see
the error signals that come from the bearings of the yellow housing and the black housing, those arrow signals are fed back to the automatic pilot, and so the plane will stay on course.
Yeah, so it's pretty epic. Notice how it just sticks in that same orientation. So again, that is the main property of gyroscopes. Let's continue now. Further now. So now the next one is precession. So this one here, even though it's being torqued, it's not precessing because it's spinning much faster and and has a lot more momentum because a lot of mass spinning relative to the friction in these bearings, which are again low friction on these, so it's not going to induce much torque on it. So going further, so precession is a change of the rotational axis of a rotating object. So basically, if the axis is here, right here, precession is going to be such that this moves it. So if that axis is actually changing. So in mainstream physics, precession is explained by the right-hand rule. And I'll quickly go over this one here. I just don't like explaining it with this setup because I think my setup is more intuitive and correct, or it goes towards the the actual nature of gyroscopes. So here is image: a spinning wheel precesses in the direction as per the right-hand rule. So here's wheel and axle supported at one end end by cord. So this is a gyroscope that can basically this is hung by a string, so it can basically go any direction, but the thing is it's being torqued by gravity going downwards like that. So axis about which the gravity torque would tend to rotate the system. So if you have it spinning here by your right-hand rule, so spinning this way, and then this is the, we'll call that the torque vector. And this L is angular momentum, basically the linear, the spin or rotational equivalent of linear momentum. But anyway, so this is rotating like that. And then by the right-hand rule, is if the torque is down, so you would use so it wants to spin it it wants to torque it this way. So you will curl your fingers like this, direction of torque due to weight of wheel, and then you'll point your thumb here, and this will indicate the direction of change of this angular momentum vector. In other words, it's basically using right-hand rule and it's pointing there. So this is right hand spinning this way. Right hand torque this way with your thumb out, it's going to be precessing about this way. So torque due to weight causes precession in the direction of change of L, so right here. So that's right hand rule, just not that intuitive. And now here is a precession of just a gyroscope that's set up like a spinning top. And we'll click this GIF right here. So there it is. So here it is. This one is precessing like that, but note a few things. It's assuming there is there's friction at this base right there. so that the base is not moving, because the center mass is there. So yeah, so basically the change of the spin axis is precession. So that's mainstream physics. Mainstream demonstration of precession that ignores friction at the base or gyroscopes rising on their own. And also, it's not rising. Yeah, it's supposed to be rising on its own. So it's assuming that there's friction here, hence it's not moving. And it's ignoring that it rises. So it's ignoring this. So that's mainstream. But now we're doing MES in physics. In MES physics, precession is explained as the spin and applied torques wanting to line up with each other, even if it means rising against gravity. And to illustrate this, I'll just draw this. Let's say you had a spinning wheel like this, and then had an axle over here, and then it goes on the top. Just to make it super simple. And let's say it is spinning like this direction, and this would be, if you use a right-hand rule, that'd be counterclockwise. All right, and this is acting as a spinning top. So you have it over here is the base, and let's say your gravity is acting upon it. It's going to be pushing it downwards. In other words, gravity is going to be trying to torque it around this direction, also in the counterclockwise direction. So in other words, so then this wants to line up. So precession is going to be such that it's going to go over to this side, such that the wheel will be pointing over here, and this is going to be the wheel. It's going to look like this. I'll just it's going to want to precess over to this side, such that you'll have this. The spin is like this. So in other words, these are lining up. So this is going to be precession there. All right, and here I'm just going to write here precession. This is going to be precession. All right, just fix that up. And then here I'm going to write this is going to be this and this are lining up. So the applied torque, which is just gravity, and the spin want to line up. All right, so that's just a general idea of how it just lines up. But then if it's spinning the opposite side, let's say we had the same setup, but the wheel is spinning on the reverse, so it's going to spin clockwise. And then let's say it's going to be, this is the axles or the base there, and it goes like that. So then now let's say you're spinning the opposite way. So again, you have the same gravity torque coming down here. So it wants to spin it this way. So this is torque from gravity. So then this is going to go reverse precession. It's going to go like that. So this is going to be precession like on the reverse direction, and then you're going to have a wheel such that it's going to look like this. Let's draw this all the way across here. And so this is going to be reversed. So if you look at it, if it's spinning this way, you're moving over, so it's going to be going this way. So again, you're going to have lining up. So this is how I explain precession. And yeah, I find it more intuitive. So let's say we have that. And but then what also happens is precession, because you're moving the gyro. Now you're moving it this way or this way, this way or this way. That also applies a torque, and this can rise on its own. That's why I do my explanation, because this one, it's not including the rising on its own in the mainstream Wikipedia explanation. So so let's say we had the gyro. Say this time it's going counterclockwise rotation. And now you're going to have, we could ignore this. So let's say it goes like this, or actually let's keep that arrow there. So, I'm going to keep that end of the gyro. And let's say it's precessing this way, because again, as per this, so we have the torque from gravity, and it's going to want to precess this way. But then this is also a torque, because it's also moving it. So in other words, this is what this is going to do is actually want to line up with the spins with the spin direction. So in other words, it actually can even rise on its own if you have the conditions proper for it. So it's gonna precess such in a spiral, such that you're gonna have a gyro that's gonna go up like this. And I'll just draw this first. So it's gonna actually rise on its own. So it's gonna go like this. Whoops. All the way up. And here I just fixed up that drawing, and so this is going to spin in the same direction. So it's going to go this way, and this is going to spin this way. So in other words, these are lining up. So you have precession is a torque. Just fix that up. Precession equals torque as well, and then this is going to line up. So let's move this away as well. It's going to go up like that. I'll just ignore that. So it's going to want to go rise upwards. Actually, it's better to do it in a spiral. So it's going to go like this, and let's draw this better last time. All right, this is going to rise upwards, and this and this are lining up. Lining up. Now, if this is the first time you've seen my videos, you might be wondering, okay, this is a unique way of describing gyros, and also where's the proof of it rising? Well, I have many videos of it rising. So here, this is demonstrated in the following experiment, which shows the downwards torque causing precession in the counterclockwise direction, since the gyro is also spinning counterclockwise. And yeah, so you have this one counterclockwise, it's going to go downwards, and then you have the lining up precession is going to go around this direction. And then precession torquing itself upwards. And precession itself acts as a torque to keep the gyro upright and rising. Again, all this until the gyroscope lines up with precession and applied torques. It's actually going to go rise up fully. And I have this on ice friction to show that it has very little friction on the at the bottom. I mean, yeah, it's very little friction, but the gyro is actually spinning not about the center of mass. The center of mass is literally near the gyro. So that, again, another part of Wikipedia which ignores the friction at the base. So when you have very little friction, it still can go on its own. So it's some magic stuff here. So tiny ice friction overcomes tiny torque from precession. And gyroscopes precess upwards on ice with 0 centripetal force. And it's the MES experiment 5. So we click it, it goes up to this, brings it up right here. And let's just do the experiment. Let's play it. All right. I just spun it up. I have it at this. Whoops. Yeah. Okay. I'm just going to speed it up. So I'm speeding it up to 4x speed, 2x. Let's keep it at 2x speed. And it's rising on its own. Whoops. Just, So notice it's not pushing it outwards. Center of mass is over there. So it's precessing like that. And it's going to actually rise fully upwards. I don't know why it's glitching out. Alright. And it's going to keep going. So precession is actually literally torquing itself upwards. And yeah, I'm just going to fast forward it more. Again, it wants to line up with the spin. Yeah, I'm just going to keep going faster. Yeah, I don't know why. I think my internet connection or something is clogging up. I'm just gonna pause. Okay, pause my OneNote. Okay, so there it is. It rose all the way on its own. So go back. And now it's spinning like that there. So epic stuff here. So it can rise all the way on its own. And then notice what happens as it's losing its spin speed. This again is for another day. But as it loses its spin speed, then it starts moving. So once it falls down. And now notice the center of mass now. I'll slow it down. Yeah, so I just put it down here. Yeah, and as it's falling now it's not, it's precessing literally, or it's turning literally about the center of mass, which is shifted away from the base. So again, that's some further stuff for gyros. All right, so that is the idea of precession. And now further demonstration can be seen in a gyrocompass type setup. Here again is a gyrocompass setup, but again the friction is way too low and there's no induced precession. I mean, the friction is way too high and there's no induced precession mechanism, so it's not really a gyrocompass. But here's what happens here. So further demonstration can be seen here. We'll go to this video soon. I have it unlisted. But basically what you have is, so torquing the gyro will want to align spin and torque directions. It will line up. And here's a stable setup. So torquing in the direction of spin is stable. So when you have this, you could torque it as hard as you want, and it will still go. But then here, if you torque it, like it's still on the same parallel direction as the spin, but on the reverse side, torquing in the opposite direction is unstable, and any deviations from horizontal will induce precession and cause the gyro to flip upside down. So you have to be very, very careful. If you torque it slightly above a horizontal, it's gonna literally induce precession and flip upside down, as I'll show. And then also here's another demonstration. Pushing the gyro down will cause it to precess so that it spins downwards. So if you push it down here, it's going to torque. The way it's going to torque is such that this wants to chase it. So again, notice always how it is. So this wants to chase after this part right here. So it's going to precess around this way and also rise such that they line up. Yeah, so that it spins downwards, but then as it flips over to the other side, if you start pressing, it's gonna so once the gyro tilts so that it flips over, a downwards force reverses precession direction, but still wanting to align spin and precession direction. So if you push it on this side now, because once you've fully flipped this over, now it's gonna want to, again, look at the torque, wants to line up with each other. So then this is gonna start going in the reverse direction, chasing after that induced torque. So let's just click this video and let's go to it. All right, so we have it over here. It's loading up. I have it unlisted. This is one of my draft experiments, just to demonstrate it. So here it is initially. So initially you just move it around, and there's no, there's nothing special about it. So it's just a regular gyro unspun. And then once you spin it up, so I have it spun up, and now just move it around. So move it around once to maintain its orientation. So we get a higher quality, at least 720. Okay. Yeah. And then if you induce, so it wants to maintain that orientation. So it's pointing there, and then I'm going to start. Oops, I'm going to start inducing torque on it. So if I push it like this, it's going to want to line up. So you can know which way it's spinning just by the direction. So that's stable. So this left hand finger up curling like that. So it's clockwise turning. So that was stable, but now if you go opposite, is unstable. So you got to go slowly, because the second you deviate, it's going to induce a torque and flip it upside down. So that is one setup there. I'll lower this volume more. Let's make this auto. Yeah, so again, you can play around with it and see what, the torque wants to line up with the spin direction, or the spin wants to line up with the torque. And again, there's stable and unstable setups. And then lastly, here I go here. If I press down, it's going to torque such that it wants to line up the spin directions with it. So if I go opposite, once it flips. All right, so push it down, it's torquing on to the other side so that it lines up with the direction. But then once you flip it, it's doing the reverse now, because it wants to, again, line up. Anyways, so that is that. So let's continue now further in our journey. So now that we understood the gyroscope properties, and now I just want to make another note here. So important note: high spin speeds overcomes small torques. Note that in the case of the gyroscope with 3 degrees of rotational freedom, the 3 degrees rotational freedom, that's this one right here. That's this guy's setup right here. Even though he's turning it, he's still torquing it, but the bearings are really smooth, so there's very little friction, and this is spinning super fast, has a lot of weight, so it's able to overcome this and not induce noticeable precession, because technically everything does induce it. So we have that. I'm just going to go back down here. Yeah, so go back down here. So note that in the case of the free gyroscope with 3 degrees of rotational freedom, the bearings provide very little torque, hence the gyroscope will barely precess as the casings are turned. If a gyroscope is spinning fast, then the gyro will precess slowly. And here's MES experiment 2. The gyroscope on the left is spinning fast and precessing slow, and the gyroscope on the right is spinning slow but precessing fast. Alright, yes, if you click this link right here, actually what I did, I actually cropped it out and made a short section of it, but you can click this for the full YouTube length video of it, and here this plays better when you open the desktop or in Telegram itself. So I have it on my Telegram MES links. So here it is. So gyroscope spin speed comparison: left is spinning fast but precessing slow, right is spinning slow but precessing fast. So the one on the left is near the beginning of the session. This one near the end. So notice the spin speed. So this one's moving very, very slowly because it's able to overcome a lot of that torque. And then whereas this one is going super, super rapidly. So this is an epic demonstration. Zoom in like that. Lower the volume a tiny bit. Yeah, so you get the idea there. I'm just going to exit, and again, that's why I follow my MES links on Telegram for more content. Let's go back here. So theoretically, if a gyroscope is spinning very fast, then it will appear to not be precessing at all. Thus, even the gyro spinning top above will act like a free gyroscope. So this one right here, if you have it super, super, super fast, theoretically, yeah, it will appear to be stationary in the air, just defying gravity. That's epic stuff there. So now let's continue and look at now how gyrocompasses actually detect true north. So theoretically, a gyrocompass can detect true north without any additional mechanisms to induce precession, since gyroscopes want to align with applied torque. So theoretically, you could just put this upside down here. This is just basic gimbal setup you could buy in the store. And then as the Earth rotates, make this a bit smaller. Yeah, as the Earth rotates, this will want to induce precession in it and line up with it. But again, Earth rotates very, very slowly, and these bearings on this conventional top, this conventional gyrocompass, or just a simple one, is very, very high, so it's not going to actually detect anything. So image a theoretical gyrocompass without additional mechanisms to induce precession. And here's another one, theoretical gyrocompasses with only 1 degree of freedom. This one can only spin about this axis, so it can only go like this or reverse. But then even then, gyros automatically align when you torque it on there like that. And this is from MES Experiments 31, which is pretty epic. Theoretical gyrocompasses with only 1 degree of freedom. Let's just play this quickly. All right, and this was an experiment by the late Francis McCabe, and to demonstrate inertia, mechanical demonstration of inertia, and also magnetism as well, how you charge, or you can electrify a piece of iron just with a current, and literally turn it to a magnet, or just have a large magnet next to small ones. They all become like magnets, orient the same direction. So it's all very, very similar. So here's initially it's all random. Yeah, it's all random as it spins it up. And then once he torques it, they all line up quickly. Okay, so there it is. Once he lines up, they all look at the gyros, how they're all random. They're all spinning up in random orientations. Once he torques, they all line up. So essentially a simple gyro compass idea. And if you put the Earth right here, think of the Earth spinning, all these line up. So video theoretical gyro compasses with Earth imposed in between. This was my earlier gyro compass video on the Debunking Flat Earth. But now I am going to, but again, they had some errors there. I had to correct them in this video. But also further, but since Earth rotates very slowly, the induced precession would either be incredibly slow or too small to overcome friction and other constraints. And certainly not basic store-bought gyrocompass setups, or gyrocompass-like setups over here with direct metal-to-metal supports with no bearings. So literally no bearing, it's just a connection. Over there, and at the bottom you'll have this one here at the bottom is just a metal rod in a hole. Like setups with direct metal-to-metal supports with no bearings, as these flat Earth disinfo agents, well, I believe they are. Why would they? Or just complete clowns here. Would have you believe here. So this is Globebusters' big channel right here on Gyroscopes. They talk about this setup right here, and they have a timer and wonder it doesn't turn at all, and deduce that Earth's not turning. So video flat Earth disinfo agents discussing a useless quote gyrocompass experiment with high friction connections that would be unable to detect Earth's rotation even if it was 1,000 times faster. Literally, I'm not joking. So here's a demonstration of the same gyrocompass they have as above, and showing that it can't detect slow rotations since static friction is higher than dynamic friction. Yeah, so when you have static friction, when you're something at rest, it's have a higher friction to push it off than once it's rolling or moving, and so on. So that's for another day. So here's a video. Gyrocompass can't detect slow rotations due to high static friction. So let's play this one. Yeah, so let's open it up. So here's that same gyro setup here. I have, again, an unlisted experiment, just a draft one. So this gyro, initially you move it, it doesn't resist any change. So you can view this as, imagine this is the North Pole, and then you'll have this there, so you're rotating there. This is how a gyrocompass should be having a North Pole. Alright, so spun it up. Like so now if I spin it super fast, notice how it wants to maintain orientation still. So it wants to still maintain, in other words, it's detecting rotation. So going back here. So if I have it fast, alright, let's go fast here actually. Okay, so I have it here. If I go fast, yeah, so if I rotate fast, it wants to aim in this direction. So in other words, it's detecting a rotation because it's relative rotation from the gimbals and that. But if I rotate slowly, look at it's turning. It's literally turning with it. So the frictions are too high for it to maintain its orientation. So it's a tiny bit precession there. But look at it, it's completely turning because the frictions are too high. The friction, yeah. So in other words, it can't detect slow rotations. If you look at it, imagine it's the Earth, it's moving with it, so it doesn't look like it's doing anything. So it turned fully over there in like a few seconds. And this is super, 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 super slow that I'm rotating. All right, so you get the idea, and then once you spin it up faster. Okay, so now once you go faster, yeah, notice it's maintaining orientation, so it's detecting relative motion from the spin. But if you go slowly, the whole thing rotates. So that's the idea I wanted to show, and then we can do some calculations of it. So my above gyroscope couldn't detect the rotation of one per 2 minutes of rotation of one rotation. Couldn't detect the rotation of one revolution. I'll just make it slightly different wording. Per 2 minutes, rough estimate. So assuming you're going to go for 2 minutes or even a minute and a half. Compare that with Earth's rotation. So Earth rotates once per 24 hours. So if you speed that up, so 10 by 10x, 10x is one revolution per 2.4 hours. Another 100x, if you just do 100x instead, that is 0.24 hours, times it by 60. That's just going to be 14.4 minutes. And this is built in a calculator in my OneNote. You can press equals space. All right, minutes. And then if you do 1000x, that's going to be 1.44 minutes, which is just faster than our slow rotation. Again, that's an estimate. It might be actually the same thing. So we're talking literally 1000x speed. This one can't detect it, 1000x of Earth's rotation. Whereas these guys are just leave it there and do nothing. So in other words, even if Earth's spinning 1,000 times faster than it is now, this experiment would not detect it, and hence the thumbs down I put. So okay, that's pretty next level stuff. All right, so now going over the mechanism for an actual gyrocompass, or how some of them use it to speed up precession or induce precession, because again, Earth rotates pretty slowly. And also go over some corrections that I need to make on my earlier videos. So thus, there needs to be an additional mechanism to induce precession and speed up the gyro alignment with the rotation of the Earth, or produce literally frictionless bearings. Yes, the other alternative is literally produce, or alternatively produce literally frictionless bearings. All right. So the easier one is just add an additional mechanism. So one such method, but also you still need, regardless of whether you have it or not, you still need very, very, very low friction bearings. So one such method is to add a tube of mercury that shifts its position as the gyrocompass lifts the tube, trying to maintain orientation. All right, so here is the setup here. So if Earth's rotating this way, from west to east, and you have so these mercury tubes along this setup right here. So what happens here is, and we can again use our knowledge of gyroscopes, want to align spin speeds with applied torques. But in this case, this is very low torque, the Earth. So as it's rotating, this just wants to maintain, because you can still get low friction bearings on this axis going into the page, or this axis like this. That isn't hard to do, just trying to get it maintained instead of processing. So it wants to maintain. So this is liquid mercury inside here, but then as it's rotating down, this wants to this wants to maintain orientation. So in other words, this is going to slightly lift the tube up. So relative to gravity, this is going to have more fluid in here, because this is lifting this up, trying to maintain orientation in space there. So in other words, this is going to be heavier on the mercury side. So this is going to induce a force down here. And the precession is such that, this wants to line up. So think of it, it's going to go, so if this diagram, if they have it spinning like that, if they have it turning this way, this means that this is going down, this is going up, that's the torque. So then this one needs to line up. So in other words, this is spinning this way and this way. So you can literally tell the direction of it. And then finally, it's going to go over to this side. It's going to be spinning this way. So in other words, it's spinning in fact opposite of gravity. So I'm opposite of the Earth's rotation. So if the Earth is rotating this way, like the clockwise, this is going to be going counterclockwise. So this is the thing I wanted to correct. So in my earlier videos, I said it was always going to be the same direction as the applied torque, but this isn't the only applied torque. This is a very little one compared to the mercury there. So in other words, this is going to go opposite of the Earth's rotation. So this is actually going to go like this. But notice how the interesting part is, it lines up with this, but it's again spinning opposite of it. This is going counterclockwise, this is going clockwise. All right, so that is one basic setup there. So image, the Mercury causes a downwards force on the left side. Thus, I'll just make this even smaller to get it all on the same page. All right, thus causing a precession, precession, not a precession, a precession such that that spin lines up with a downwards force. Thus, in this case, the gyro rotates counterclockwise and opposite of Earth's rotation. And the following image right here shows a gyro compass with and without the Mercury tube. Note that this image is indeed correct. My earlier videos I said it was wrong, and that the image I used in my earlier videos is wrong. So the image I corrected was actually wrong. This is right. And the gyro compass without the tube is not a free gyroscope, as I incorrectly stated before. So this is still a gyro compass right here, but without the induced precession. And another issue is when it's perfectly lined up with the east to west, it's not going to want to precess anyways. It just wants to hang in the air there. So here's a ship anchored on equator, axis of gyroscope points east to west. So you have east and west like that. And so at 1 hour, it's going to go 15 degrees. So Earth's rotating from west to east at a rate of 15 degrees an hour. So at 1 hour, you're going to have 15 degrees rotation like that. It wants to maintain. So in this case, there's no induced precession. It just wants to maintain. So it looks like it's rotating, so it's detecting it and so on. So that is a gyro compass without any induced precession. Again, that's another issue, is not only the bearings, you're going to need very high quality bearings to do induced precession naturally if there's a deviation, but even then when it's perfectly aligned, it's going to just want to maintain orientation. But we want to point this to the north pole there. So here is the Mercury tube setup right here. So, and this one is with the spin directions. So again, this was the spin is like this way, as we stated here. It spins opposite or counterclockwise, opposite of the Earth's rotation. So here's the Mercury tubes as it wants to maintain orientation. It's going to be lifting this tube, but then the Mercury flows to the other side. You're going to have a downwards force here, upwards. So in other words, it's going to precess such that these line up, such that this goes lining up with that downwards force there. So that's the direction of precession, and it's going to be opposite of Earth's rotation. So this, in other words, counterclockwise versus clockwise. So rotation of Earth, and now it's pointing, now the gyro compass is pointing to the north. So rotation of Earth carries ship from west to east, regardless of ship's own movement, so that the axis of gyroscope always becomes tipped from horizontal unless it is pointing due north. And now it's not being tipped anymore because it's in line with the rotation there. But again, Earth's rotation is very low, so torque from it isn't that high. So even though this is technically unstable equilibrium, this is very low. And even then, even if it shifts the other way, the Mercury tube is going to force it back to the same direction. So image gyro compass without the Mercury tube wants to maintain orientation above, and gyro compass with a Mercury tube wants to align opposite of Earth's rotation. And alternatively, adding a weight at the bottom of the gyro compass will torque it downwards such that the gyro will precess to align with Earth's rotation. So again, you can have a different gyro compass setup here. This is the one I was thinking about before. And this is from an actual, this is Steering Mariners. This is an actual guy that works in the shipping field or industry and so on. So he knows full well how these operate, but again, not my explanations though for it is a bit different. So anyways, here, so this goes wants to go in direction. So if you have this Earth is rotating this way, so now what you have is a weight added. So now you can induce precession here. So as it wants to align with, or as it wants to maintain its orientation as the Earth rotates, it's going to lift the weight. So it's going to induce a precession or a force down here. So the precession direction is going to be, so the torque is going to be such that it's going down here, up like that. That's torque. So in other words, it's going to be a clockwise torque. And so then this gyro is going to want to precess such that it lines up with this setup here. So with this, like that. So it's going to precess this way, assuming it's, assuming it's rotating that same direction there. It's gonna go all the way across to here and line up with Earth's rotation. So Earth's going this way. This torque is pushing it down. So it's going to want to precess either this way or this way, depending on which way it's rotating at the start. And then line up with this spin direction there. So in this case, it is spinning with the Yeah, with the Earth. And note the flywheel in this case, this video says that flywheel spinning anti-clockwise when viewed from the red axis side. So from here, anti-clockwise would mean it's going to go opposite this way. So if spinning like that, this is going to be literally the right-hand rule. So your fingers are curling around this, and that's anti-clockwise. So then if this is down, this is going to want to spin such that it's going to want to precess this way, such that this red will be pointing north over to there. So that's the north side. And then you'll have the direction is going to be such that, yeah, the precession, you're going to precess like this, such that this is going to line up like this. And this is the direction that it's spinning is going to be this way. Yeah, so it's going to be doing like that, lining up with that applied torque that was this way and this way. So that is the way it's going to move. All right, and continuing further, so a video inducing precession in a gyrocompass by adding a weight at the bottom caused the gyrocompass to align in the direction of the Earth's rotation. Yes, in the direction, it's supposed to opposite. So this is pretty much how a gyrocompass works, but further technical operating details can be found at the Steering Mariners YouTube channel. So that's a pretty interesting channel. They have 50,000 subscribers as well. It's pretty epic. Alright, so going further, so further corrections to my earlier videos. As stated earlier, the image I used to explain gyrocompasses as my, or actually I worded better. So here's the image I used to explain gyrocompasses as my wrong, has. Here's the image that I used that has my wrong quote corrections applied to it. So here's the image I used several times in the Debunking Flat Earth videos and my anti-gravity videos. So MES Note, the top picture is a free gyroscope, bottom is a gyrocompass. That is wrong. They're both gyrocompasses. This one's technically both, but this one doesn't have induced precession mechanism. And your MES correction, spin direction should align with the Earth's rotation. Wrong. This one has a Mercury Tube set up, so it goes opposite. So the image, this is the MES notes in red are wrong. The unedited photo is correct to show the gyrocompass aligns opposite of Earth's rotation. So another error I made in my early videos was stating that the compensator weights on the World War II gyrocompass were what induced precession. This is again wrong. This is wrong. The compensator weights are just as the name states. They are added to compensate, that's the key word, for the weight and balance to ensure the gyro assembly is perfectly balanced by weight. So they added these weights on top of that frame so that it has the exact same weight on this axis or the other axis, so don't need to worry about it tilting or so on. Just make it all perfectly balanced. So design of the Sperry MK XIV gyrocompass, etc. And then also, if you watch the video to the end, I don't think I ever did. I don't know why. So compensator weights to balance the weight of the gyrocompass. And yeah, I didn't do it because I never did a video specifically on gyrocompass. I just added some notes about it. So if you scroll over to the rest of the video, so 2 Mercury tubes attached to the gyrocompass to induce precession, and here's a Mercury, they call it a Mercury ballistic. So you have a gyrocompass right here. So if it's maintaining its orientation relative to the Earth, so then you'll have the gyrocompass, it's going to be aligning like this. And then as this is going to want to raise this to maintain orientation, so then Mercury is going to flow out to the other side. So it has 2 tubes, one on each side. So one on the, this is going to be on the west and east side, or east and west sides like that. And then it's going to induce precession, and it's going to go opposite of the Earth's rotation, not in line. And then here is the Mercury tube shown in the complete gyrocompass assembly. And here is the compensator weights on this side. There's the Mercury tubes, and they're connected to each other through this like flat bearing or flat connection there. Anyways, that is all for today, and yeah, I just wanted to go through this, wanted to clarify it. But again, the videos and the Debunking Flat Earth, they all still stand. It's just that the gyrocompass, there's just a bit more detail on it, how it precesses, and it goes opposite of Earth's rotation, because again, Earth's rotation is a very small torque, so any induced ones will be bigger. And yeah, and faster to detect true north. Anyways, that is all for today. Thanks for watching. Hopefully you enjoyed, and also enjoyed my MES physics explanation of gyroscopes and gyrocompasses and spinning tops. Again, this is rises on its own. So until Wikipedia includes that in theirs, I'm gonna keep calling it MES physics. Anyways, that is all for today. Thanks for watching, and like always, you can download these exact notes and link that's in the description below, as well as view these notes on the Hive blockchain. Anyways, that's all for today. And yeah, stay tuned for another math easy solution.